with two different injection dose of the nanoparticles. You can see after the injection, the signal becomes darker compared to the before injection. And we also measure the relaxation time of the area, and you can see here, compared like after injection, 24 hours after injection of the particles, the relaxation time significantly reduced compared to the one before injection. So these are two different injection doses. And we test the anti-inflammatory effect of our nanoparticles in the liver. So here you can see the particle can suppress or reduce the expression of inflammatory biomarkers. Here TNF-alpha, COX-2, and iNOS as well. And these are the histology images that show that with the treatment with our particles, the particles have to reduce the inflammation and reduce the fibrosis of the liver. So this is the normal liver without any treatment, and this is the liver treated with CCO4. You can see lots of fibrosis and inflammation here. And after the injection of the particle, we can see these are two different injection doses. This is the lower dose and this is the higher dose. And we can see that when we treat the mouse with the particle, we can reduce or inhibit the fibrosis here compared to the control. And the next example is silver-coated iron oxide nanocluster for diagnosis of thrombosis. So the core is iron oxide and the outer layer is silver. So we synthesize iron oxide core and then we coat with silver. And this particle can be used for MRI imaging. It can quench ROS and it can do photothermotherapy for cancer and for thrombus as well. So the particles had a popcorn shape like this, and the size is quite uniform. It has strong absorbance, wide range of wavelength, and up to the near-infrared range as well. And the particles can do MRI imaging. You can see the signal increase. The dark signal increase in MRI. And the particles can quench ROS as well. You can see in the cells, in macrophage, when we treat the macrophage with the particles, it can suppress the level of ROS here. And you can see the image here. So without the particle, high ROS level, and with the particles, low ROS level. And the particle is not toxic to the cells at the treatment concentration dose we use in this study. So we also use this particle for thrombus imaging. You can see again the thrombus at the bottom of the ependymotic, and we can see the particle bind on the surface of the thrombus and show up as the dark signal on the surface. And because the particles had a strong absorbance around 800 nanometers, we use 800 nanometer laser light to induce the thrombolysis of the clot. Here is the control blood clot, and these are the clot with the nanoparticles and treated with the laser. So you can see in the presence of the particle and the laser, the blood clot size is significantly smaller than the control one. It means we can lyse the clot with the treatment of our particle and the laser. So this video just show you the effect of our nanoparticles. So in the presence of the particle and the laser, it induced the acoustic cavitation, and the energy released by this microbubble help to break the clot. We also use this particle for the thermotherapy of tumor. So you can see here with the treatment of the particle and the laser, the viability of the cell significantly reduced. So Shaprin Moon, my postdoc, is currently working on this project focused on the cancer. And we show that the particles do not stay remain long in the body. So you can see after 1 day of injection, the particle had high accumulation in the spleen, the blood, and the liver, but we cannot detect in the kidney or the heart, very low amount. But then after 7 days, you can see the level of the particle in spleen, liver, and blood reduced to baseline level. And we also proved that the particles are biocompatible in mouse organs. So this is the control mouse, and these are the mouse injected with the particle at different time points, 1 day, 3 days, and 3 days. So you can see there is no obvious toxicity on the mouse organs. And we also developed polymeric nanoparticle for the treatment of vascular calcification. So this particle, the beauty of this particle is they are very stable at low pH, but when we put them in the high pH, on the neutral pH like pH 7.4, the physiological pH, it can gradually dissolve into polyamino acid, and then it can inhibit calcification and dissolve hydroxyapatite. So how to treat the calcification in vascular wall. So I will not talk more about this today, but hopefully in the future. So that is the end of my talk, and I would like to acknowledge all the people involved in these projects, on the organizations, and on the funding agency, and also thank you to all of my group members, my students, and my postdoc, and thank you for your attention.
Thank you very much, Professor Ta, for a very interesting talk, which went a lot of the applications of these materials that we're looking at. So I know that there wasn't everyone in the room when we first started this talk, but if anyone's got any questions, please feel free to drop it into the chat. And I'm happy to ask those questions. We've probably got a couple of minutes for some questions, and I might just lead off. So I thought your materials where you were looking at iron oxide, cerium oxide, nano cocktails was quite interesting for the ROS distribution. The one question I have is that you use a lot of fluorescence imaging to demonstrate some of the assays, especially around the ROS, but cesium's generally quite paramagnetic as well. So do you get any quenching of the fluorescent assays from some of these nanoparticles that you've got, so sort of as an artifact?
I don't really get what your question. Like you said, you asked whether I see any quenching effect.
Well, the fluorescence, I mean, the fluorescence obviously use a fluorescent assay to demonstrate the ROS. So as you have more fluorescent, you have more ROS being formed. And then when you put your particles in, you see a quenching or less fluorescence. But do the particles themselves quench the fluorescence as well? Because cesium's paramagnetic and should lead to a quenching of that fluorescence as well.
Oh, okay. Yeah, I got your point now. So your question is whether the particle quench the fluorescent, not quench the ROS.
Yeah.
Good question. With this, let me see. Really good question.
It may just be something to think about. So, I mean, with most of the systems,
I don't think it's quench, because I don't think the particle quench the fluorescence, because we do have the experiment that, whether I have it here, let me show.
Yep. So here, so this I definitely agree with. So silver's not going to quench it. I was just more wondering about the cesium particles themselves, because the cesium itself should be quite, should lead to some quenching of the fluorescence. It might just be something that you need to consider at some stage as well. So we also have a couple of other quick questions. So do the metal oxides need to be of a particular size to be effective?
Sorry, say again.
do the metal oxides need to be of a particular size to be effective?
Do the nanoparticles need to have a specific size?
Yes.
So it does. For example, it depends on the application. For example, if we want for iron oxide nanoparticle, for example, so if we want to have the dual contrast, we need to go to the very small size. So here we have 3.3 nanometers. So this one can have both dual positive and negative contrast. But if we go to the very high size, like larger size, like about 50 nanometer, for example, we will not be able to have the bright contrast or T1 contrast. We only have negative contrast, not positive contrast. So the size does have the effect on the properties. So it depends on the functionality that we need to tune the size.
Yeah. Thanks. And just a final question. There was a question that asked, how does the body remove these nanoparticles? So if you're doing this in vivo, how are the nanoparticles cleared from the body?
How the particles are eliminated out of the body.
Yep.
So the mechanism that the particle eliminated out of the bodies are not like we haven't investigated deeply into the mechanism how the particles are eliminated out of the bodies. But in some of our projects, in some of our study, we prove that the particles, like some particles, do not retain for long in the body, like the latest study that I just showed you. So here, this one. So after 7 days, so the level of the particles in all organs go to the baseline.
Okay.
Yeah, but the mechanism we haven't investigated deeper into that area.
Okay.
Yeah.
Well, I think that's about all the time that we have at the moment. So just thank you once again for a wonderful talk and for being part of this this meeting that we've got going. So thank you, Professor.
Thank you very much.
Okay, so now we've got a lineup of excellent ECR speakers, and that's going to be kicked off now by Maricruz Gonzalez, who's a postdoctoral fellow at the University of New South Wales. I hope I said that your name correctly then. So she's going to be speaking to us. He's going to be speaking to us today about the separation of electronic and ionic conductivity and reduced graphene oxide, polyelectrolyte polymer hybrid nanocomposite films. So over to you, Maricruz. You have to unmute your mic.
Okay. Sorry, now I'm here.
Hi.
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 Thank you. Thank you, James.
Okay.
First of all, good morning, everyone. Now I'm going to talk about the project that we have in Saborio in conjunction with KMD. And basically, we are producing the separation of electronic and ionic conductivity in polymer reduced graphene oxide polyelectrolyte hybrid nanocomposite films. Let me introduce you to the concept of composites. A composite is a material that contains a filler dispersed in a matrix that is a continuous phase. And this filler wants to have intrinsic properties that later on are going to affect the final properties of the composite at the end of the synthesis. It is important to of this filler with the continuous phase because in this way we are going to manipulate and ensure the quality of the dispersion of this material. And basically all these properties of the filler are going to be selected according with the application that we want to give it at the end of the synthesis. And yes, the nanocomposite will have a unique property due to the additive effect of the individual components' properties. Let me decrease my image here. Yeah. Now, in our group, we were developing RGO polyelectrolyte, RGO polymer nanocomposite. This polymer butylectrolyte and styrene, and we were being able to see, you can see in this TN image, the segregation of the RGO particles that form a very well-defined pathway of electron delocalization due to the percolation of these RGO particles. And then we can see how this electron delocalization happens through the sp2 orbitals along all the reduced graphene oxide. then we must to highlight that the filler who gave us the electronic conductivity in this polymer nanocomposite. In the next step, we are going to add polyelectrolytes, and this is the main topic of this presentation, is the addition of polyelectrolytes to that composite that contains RGO in a matrix of polymer. And the polyelectrolyte is being defined as the polymer containing repeating anionic or cationic groups that are going to help the solid to be dissolved in an aqueous solution, or liquid polyelectrolytes such as polyionic liquids. The polyelectrolytes can be divided according with the charge in cationic polyelectrolytes, anionic polyelectrolytes, and suianionic ones with positive and negative charge in at the same time in the polymer. And as well, we can classify according with the charge location. If the charge is located in the main backbone of the polyelectrolyte, we are going to call this as a polyionine, as is the case of the isobenzene groups. And we have as well the classification according with the shape as a hyperbranch and cone shape. In our specific case, we were developing a nanocomposite with lignosulfonate that contains a sulfonate group that is negatively charged. And in this case, we are going to call this as an anionic polyelectrolyte that is going to interact with a counter ion of sodium, and this sodium counter ion is going to help us with the mobility, then is going to give the ionic conductivity in our nanocomposite. This lignosulfonate is going to as well have substitutes of lignin that is going to give the hardness to this polymer and through hydrogen bonds. And as well, we were studying the polystyrene sulfonate that is a linear polymer polyelectrolyte containing sulfonate groups that is going to interact with sodium as well through electrostatic forces, and is going to give us the ionic conduction to the nanocomposite. Well, the polyelectrolyte nanocomposites were first developed by Nicholas Khodabandeh in 1996. He was synthesizing polydimethyl ammonium chloride, that is a cationic polyelectrolyte with reduced graphene oxide. And he observed that the exfoliation of the graphene oxide in aqueous solution before the synthesis of the nanocomposite was very well dispersed. And he attributed this due to the repulsion of the electrostatic charges of the polyelectrolyte that are intercalated in between these sheets of reduced graphene oxide. Later on, another of the applications are very important in case of the use of polyelectrolytes is the catalyst. Nowadays, in reactions as an oxygen-reduction reaction in fuel cells, in the cathodic side, certain components of carbon allotropes are being functionalized with polyelectrolytes. For example, in this case, we have a positive charge polyelectrolyte that is going to withdraw the density of electrons and is going to leave positive domains in the carbon allotrope. In this case, is graphene oxide. And we are going to have a higher current of oxygen coming to the surface of this cathode, then the catalysis process is happening in this reaction. In terms of the conduction, we are having that the polyelectrolyte combining multilayer with carbon allotropes as well is going to increase the conductivity, and we are going to talk about it in the next slide. The synthesis technique for these multilayer films that we were discussing before is happening through a process of substrate immersion in different kind of solutions that are active. We call active material because are electrically conductive. In this case, we can use polyelectrolyte of carbon allotropes solutions, and we are going to immerse this substrate several times until the desired thickness that we needed. And in between this process, we need to wash and dry several times before another layer is going to be added. Then in terms of the layer by layer techniques, nowadays we have new techniques that help the simplistic immersion. For example, we have drop casting, spray assisted spin coating, and even electrochemical techniques are being used for layer by layer film formation. What is the advantages? The advantage of this technique, one of these is the control of the thickness. We can define the thickness of our nanocomposite, and we can, with this, for example, modulate properties as electrical conductivity. As well, another things that are not too positive is that we require the longer time processes. As well, we have more risk of contamination because the manipulation of the sample, unless we are using a robotic technique. And as well, the Alkane required is higher. As a response to this technique, we suggest soft free emulsion polymerization, in which we are going to produce a latex that later on is going to be physical mixed with a graphene oxide polyelectrolyte aqueous solution. And then finally, we are going to be able to cast and form nanocomposite films. Specifically, the reaction requires, in our case, the monomer of polyelectrolyte and benzyl methacrylate. And in this case, we have a ratio of 50-50 weight percent. And why this ratio? Well, this ratio is being selected because allow us to drive ambient temperature due to the low TG. And it's important to denote that the reaction happens in presence of KPS at 70 Celsius during 6 hours. The graphene oxide content is 5% weight, 5%, and lignosulfate and polystyrene sulfonate in a range of 2 to 50% weight. Well, and then how we form these nanocomposite films. First of all, we have the latex that before we were mentioning, we produce through soft free emulsion polymerization, and the particle size is around 500 nano. Later on, we physical mix with polyelectrolyte graphene oxide aqueous solution, and we are going to have onto a glass slide and dry during 48 hours at room temperature. And we are going to obtain a film thickness of around 10 microns. After that, we are going to thermal reduce the graphene oxide that is contained here to improve the or to produce the electrical conductivity. And we have that the thermal process happens at 160 Celsius at during 24 hours. As well, we were able to produce freestanding flexible films, as you can see in these two images. And well, finally, what about the electronic conductivity? Well, basically, we were able to distinguish between these two through electrochemical techniques such as lunar subvoltammetry and impedance spectroscopy. And basically, what we are showing here is the conductivity versus the percentage weight of lignosulfonate. We can see how the ionic conductivity is higher than electronic conductivity, and this was some result that surprised us because basically we expected a higher electronic conductivity due to the mobility of the electrons better than ions. But we are part of a few groups of researchers that already are claiming that we have higher ionic conductivity than electron conductivities. As well, it's very important to highlight that we obtain very high ionic and electronic conductivities for a hybrid material with non-conductive polymers such as polyelectrolyte and benzyl methacrylate. And both electronic and ionic conduction, as you can see here, decreased with increasing the lignosulfonate. The excessive amount of lignosulfonate, as you can see here, more than 10%, is going to produce a decrease of the conductivity due to the agglomeration of the lignosulfonate. In case of the polystyrene sulfonate, we have the same trend. Conductivity is higher than electronic conductivity. As well, it's impressive that we're having this high ionic and electronic conductivity, taking into account we are using non-conductive polymers. And then both electronic and ionic conductivity decrease with increasing the PSS content. And in this case, the aggregation of the PSS is not as prominent as for LS. And as you can see, it's evident because the change of conductivity versus a percentage of PSS is lower than in case of lignosulfonate. And what about if we compare the electronic conductivity of LS and the ionic conductivity of PSS and LS? Well, we can see that, for example, in case of the LS that is being represented with as red spheres in both cases, this is the lignosulfonate, is going to have a higher electronic conductivity versus the electronic conductivity of the PSS. And as well, we can see that the effect of the polyelectrolyte content is stronger in case of the lignosulfonate. We can see the decrease is more drastic than in case of the polystyrene. And in case of the ionic conductivity, we have that the ionic conductivity in the case of the PSS, the ionic conductivity of the lignosulfonate. And again, we can see that the polyelectrolyte content is stronger for lignosulfonate than polystyrene sulfonate. Then what we were able to get here was, well, we synthesized by soft-free emulsion polymerization, polymer reduced graphene oxide, polyelectrolyte nanocomposites. We were able to separate the ionic from the electronic conduction from polymers with lignosulfonate and polystyrene sulfonate. We were able to distinguish or to determine which conductivity is higher in each the polyelectrolytes. For the nanocomposite containing polystyrene sulfonate, we have a higher ionic conductivity, and in case of the in case of the nanocomposite that contains lignosulfonate, we have a higher electronic conductivity versus the ionic conductivity. As well, something interesting is that in case of the nanocomposite that contains polystyrene sulfonate, we have a higher and even surpass the value of the ionic conductivity for polymers with lignosulfonate. And until now, we are working in trying to elucidate the mechanism that is happening and produce this kind of trend through TEM, SEM, and so on. We already are working in the application of these materials since the high ionic conductivity, basically in electrodes for energy storage devices, but as well can be used for solid electrolytes and energy storage devices. I would like to say thanks to all my colleagues that helped me during this project, and thanks to KMD Centre of Advanced Macromolecular Design and Royal Australian Chemical Institute for allowing us to discuss science in this Festival of Polymer. Thank you so much.
Thank you very much, Maricruz, for a very, very interesting talk. We're already starting to run a little bit over time. I know that there has been some questions in the question and answer session. We'll pass those on to you, and hopefully you can get in contact with the people asking them and answer them in person. Okay. Thanks again for a very interesting talk.
Thank you.
Okay, so moving on to our next talk. We now have a PhD student talk. So it's Matthew Urquhart. Hopefully you can hear me, Matthew. Yes, excellent. And he's from Monash University, and he's going to be speaking to us about, I'll read off your slide rather than off the title, trisulfide cross-linked polymer assemblies. So handing over to you, Matt.
Great, thank you, James, and hello to everyone listening. I'm looking forward to sharing the progress I've made so far in the synthesis of trisulfide linked polymer assemblies. So the role of hydrogen sulfide as an important gaseous signaling molecule has only really been realized in the past 20 years or so. Before this, it had a pretty bad rap as a pungent, foul-smelling, toxic byproduct of industrial processes. However, recently it's been shown at much lower concentrations to exhibit extensive physiological effects, including anti-inflammatory and antioxidant behavior, among others. So this has really inspired research groups to look to explore its therapeutic potential. However, as you might imagine, the direct inhalation of hydrogen sulfide gas is an unfeasible and unattractive delivery means. So that's where we need hydrogen sulfide donors to release hydrogen sulfide in the body where it's needed. This space really started off with some small molecule H2S donors, the simple of which is sodium sulfides, which, although easy to employ, they don't really accurately reflect the slow and continuous release of hydrogen sulfide, which you see from endogenous processes. This turned to some more small molecule slow release hydrogen sulfide donors, which release hydrogen sulfide on a more physiologically relevant time frame. Although, much like small molecule drugs, they're limited by inherent poor water solubility, high toxicity, and rapid clearance. This paved the way for macromolecular H2S donors. So often what's been seen in really the last 10 years or so is that the conjugation of a H2S donating group to a macromolecular scaffold affords better biological profiles, reducing toxicity and extending the release period. So this is a space we're particularly interested in, especially so in the trisulfide compounds. So this is largely inspired by some garlic chemistry, where allyl, an abundant component of garlic, decomposes into diallyl trisulfides, among other things. Now, diallyl trisulfides are susceptible to cleavage by thiols such as glutathione to release hydrogen sulfide via a pethiol intermediate. So the trisulfide cleaves and we get H2S from it. So we're interested in the chemistry of these compounds. And this area really started with Fran Erkol's work back in 2017, where she conjugated a polyethylene glycol to a cholesterol via a trisulfide bridge. And more recently, as Nam presented on last week, we've looked at introducing a trisulfide bearing monomer to increase the donating capacity of these materials. Today, I'm going to be talking about the next step that we're taking in this area, and that's the synthesis of trisulfide-linked polymer assemblies. So it's anticipated that these materials will have all the aforementioned benefits of macromolecular donors with some added advantages. These advantages include being able to tailor the water solubility by customizing the hydrophilic corona, as well as having multiple trisulfides per assembly. So we've increased our H2S donating capacity exponentially using this approach, as well as it's anticipated that they would have controlled H2S release kinetics. This is due to the releasing moiety being in the center of the core, restricting access to the trigger. And finally, much like disulfides, it's expected that upon reaction with thiols, the trisulfide would cleave to disassemble the polymer assembly. This is something that we're particularly interested in, not only for the release of H2S, but also the release of any encapsulated material, as the co-administration of hydrogen sulfide with doxorubicin has actually been shown to reduce its off-target effects. So the approach we took, it was a simple arm-first star polymerization to yield a trisulfide-linked star. This cross-linker here isn't commercially available, so we had to synthesize it in the lab using some phthalamido chemistry that we've established. So bisphalamide can react with one equivalent of thiol to give this disulfide phthalamido compound, can bring in another equivalent of thiol to give us our trisulfide. In this case, it's Bock protected, so just a simple Bock protection, and acrylation with acrylyl chloride gives us our trisulfide cross-linker. NMR confirmed we've got a reasonable yield product. We can see the E protons here next to the trisulfide bridge, although we do have a little bit of tetrasulfide impurity in there. To confirm the star synthesis was adequate, we went back and used a commercially available disulfide bisacrylamide, and the chemistry of this is quite well known. So starting with our PEGA arm, after 24 hours of star reaction, we see good incorporation of the arm into the star, and we were able to purify this back out to get our nice disulfide star. So we thought we'd take the same approach with the trisulfide crosslinker. Again, starting with our PEGA arm, after 24 hours of reaction, however, we only see a very slight increase in the molecular weight of the arm, no star formed, and a significant amount of crosslinker still present. Taking this reaction out all the way to 120 hours, even after the addition of more aliquots of initiator, we see that we've still got some crosslinker present, although it has reduced, and only a minor increase in the molecular weight of the arm and no star forming. So this was a bit disappointed, but we wanted to take a bit of a closer look at what was actually happening here. So we purified this reacted arm back out, and the NMR told us a bit of an interesting story. So these broad vinyl protons here are indicative of a pendant polymeric vinyl group. So the crosslink is likely added on one side to the growing chain, although it hasn't crosslinked to another. This is further confirmed by signal in the trisulfide region here. So we've had some incorporation of trisulfide in our product. What was interesting, however, was that we also saw some disulfide signal, even though we didn't include any disulfide in our initial reaction. So this was a bit surprising. However, looking back into the literature, it's likely that the trisulfide's undergone a form of cleavage by radical displacement, this giving us the pethiol radical. Now, in theory, this pethiol radical is capable of reinitiating polymerization. However, I think what's more likely is that it's actually terminating polymerization, capping onto the end of the propagating polymer and introducing this disulfide signal into our product. So this wasn't quite what we were desiring, although considering we do have some trisulfide, we examined the H2S release capacity, and after the addition of cysteine in this case, we do see some H2S release. So not a completely bad result, although we determined this wasn't really a feasible means to have our cross-linked material. So we turned instead to Bluntay salts. The chemistry of Bluntay salts is quite well known, and they're formed by a simple reaction of alkyl halides with sodium thiosulfate. They're a useful intermediate in the production of thiols, thiocyanates, and sulfides, although what we're primarily interested in is the formation of trisulfides. So the reaction of two equivalents of Bunte salt with sodium sulfide rather, gives us our symmetrical trisulfide. This work was really pioneered 60 years ago now by Brian Milligan just down the road at Cyro in Parkville. The approach that we were taking is a block copolymer of PEG in the corona and vinyl benzyl chloride to form the core forming monomer. We then react this with sodium thiosulfate to give our Bunte salt, cross-link with sodium sulfide to give our trisulfide link material. First set off to confirm this chemistry on the monomer. We can see the upfield shift here is indicative of good Bunte salt formation. We can take this further with sodium sulfide to give us the trisulfide that we desire. So that was a good initial result. We can show this also on a homopolymer of vinyl benzyl chloride. See good reaction with sodium thiosulfate to form the Bunte. Now if we take this Bunte salt, we'll look onto the model system, which is here. So this is the PEGA. So we extend this with vinyl benzyl chloride and then react again with sodium thiosulfate. So this is our copolymer that we desire, PEGA, Bunte salt. We take a sample of this and react it with sodium sulfide. And we have a cross-linked material, trisulfide cross-linked material. React this with cysteine to release H2S. And quite pleasingly, we see that we have a release profile which is consistent with trisulfides being in the core of the assembly. So that's where this work is at the moment, and we've still got a bit more work to do. However, it's promising early results. So we're going to look more closely into characterizing the cross-linking efficiency of Bunte salts, examining both the assembly and disassembly, looking to determine encapsulation potential of maybe some chemotherapeutic, and looking to tune this H2S release capacity. So just finish off with a summary here. The synthesis of H2S donating macromolecules is a fast-growing field and one we're particularly interested in. The presence of polysulfides in radical polymerization can cause potential complications. We saw this with the incorporation of disulfides in our product. However, the use of Bunte salts provides a relatively straightforward approach to preparing trisulfides. Last slide, I just have to thank my supervisors, well, especially John and Fran, who have contributed to the progress of this project and for the ongoing support. A special thank you to my colleague Nam, who's just submitted his PhD, so congratulations Nam. And of course, thank you to Mikey Whitaker for the ongoing advice and mentorship, and of course the funding partners. So thank you.
Thanks, Matt, for a very, very nice talk. We've got a minute or two if there are some burning questions that you want to ask Matt while we're live now. I got one that I'll sort of lead off with. When you're designing your delivery systems, how much do you have to play with the core to, because I guess you're making a nanoreactor so that you can get this H2S release. But what's the driving force for, say, the cysteine wanting to come into the core as well as opposed to staying out in the aqueous as well? So do you have to really tune that core before you put those linkages in?
That's definitely something we're looking at, to either to copolymerize with styrene to sort of restrict access to the core, or the opposite, to allow more in. That's something we're looking at in terms of tuning the release profile, so restricting that access to the trigger.
Okay, we've got one question. So we've got a question here from Lewis. You mentioned at the start that some of these trisulfide compounds can be found in garlic. Is it possible to extract these and use them as a sustainable source for these sort of materials?
So the form that's found in garlic is diallyl trisulfide. So that is an interesting material. However, it's poorly water soluble. So it doesn't have as much application as some of the water soluble macro molecules. However, garlic extract has been studied extensively as a therapeutic. So certainly has some use.
Well, excellent. Well, I think that you should be congratulated on doing a good job up to date, and I think your supervisors have done a good job to sell you on doing a project working on hydrogen sulfide as well. So thanks again for a really nice talk, Matt. Okay, moving along. Our next speaker today is Salma Ahmed from the University of Queensland, which we have. And she's going to be talking today about dual drug delivery of chemotherapeutic agents using targeted pH-sensitive vesicles from self-assembled degradable amphiphilic di-block polymers. So over to you, Salma.
Thank you so much for the introduction. Let me start by saying, you rock. This is actually, is it moving? Yeah. Let me start by saying you rock. This is a sentence that we use if you want to describe something durable, something solid, something that lasts for ages and ages. Inspired by such things that last forever, we have been using polymers in different applications and different aspects in our lives. Some of the best examples of these polymers are polyvinyl acetate. These ones have different applications in industry and also in constructions, and they are really very versatile. The problem with these is that they are unbreakable, undegradable, which means that they will have a bad impact on the environment in the long run, and also this will limit their application in the area of drug delivery. Now the question is, similar to the same source of inspiration, rocks, is there a way actually to degrade these undegradable polymers? The answer is yes, actually. Similar to this rock, you see that we have put different rods in the face of the rock, and then we started hammering it until it degrades. And it would be really cool if you can do the same with vinyl acetate. So essentially, if we incubate the vinyl acetate with MDO monomers, and then we design specific chain transfer agents, and via means of raft polymerization, the ring of the MDO will open, and then we will introduce ester bonds that are distributed randomly in the backbone, carbon-carbon backbone of this polymer, leading hence to the development of degradable polymers in here. The question here, can we make this design fancier? The answer is yes. If we can conjugate the CTA with a or amphiphilic molecule, then we will get ourselves a nice degradable, versatile di-block of polymer that can potentially be used for the application of in the area of drug delivery. Now, to break the chemistry, essentially we designed this CTA that has a functional alkyne end group, and then we started from a methoxy peg. We changed the length of this hydrophilic block, and then we did treatment through methylation reaction, followed by azidation in order to have this functional end group. And then we had a click reaction in order to form our di-block polymer. This is one example of the characterization data that we have for MALDI-TOF. It shows you how beautifully they simulated versus the actual obtained spectra overlay. Following this step, we incubate the CTA with the MDO and vinyl acetate, as we said, in order to get this beautiful degradable block. However, if we want to make the design even fancier, we can introduce actually a functional monomer, which is vinyl bromide to this collection. The vinyl bromide can actually be turned into vinyl azide. Hence, it can be clicked then with Cy5, which is a fluorophore that we can use to track the di-blocks wherever they go. This means that actually this polymer or these di-blocks are ready for use in the area of self-assembly and the formation of nanoparticles. Now the question is, what nanoparticles are we looking for? We want to make something that's stable, biodegradable, and have a prolonged circulation in vivo and in vitro, and also it includes simple formation steps. The natural candidates are micelles, because they can encapsulate hydrophobic drugs within their hydrophobic cores, and also they can be decorated with targeting ligands and imaging probe. Another good candidate is polymersomes. Polymersomes are the polymeric equivalents of liposomes, which means that similar to micelles, they can encapsulate hydrophobic drugs, but also they can encapsulate hydrophilic drugs within the aqueous core of the polymersomes. And similar to micelles, they can be decorated with targeting ligands and imaging probe. So we should keep in mind that varying the length of the hydrophilic lipophilic blocks will result in different type of nanoparticles, ranging from the small micelles into forming the polymersomes. And there are numerous factors actually that contribute to what type of nanoparticle do we get. So I'm not going to talk here about how to tune these factors together. This will come soon in a future publication. But here I'm going to focus more on the synthesis of polymersomes. Essentially, any of these blocks, if you incubate them with the drugs that you want to encapsulate in a suitable solvent, then start to introduce PBS or water slowly in a solvent switch method, then you will get your desired nanoparticles. Following that, you can actually cross-link them. In our case, we used PEG DBC or PEG because we can then make use of the vinyl azide polymers that are still there. Following this step, we can just do dialysis to get rid of the free drug and also the free solvents that we don't want them to be present in our nanoparticle systems. And also we can conjugate the EGFR bispecific antibodies in this step, making use of the methoxy end in the PEG molecules. After that, we have our nanoparticles ready for use and ready for different applications in vitro and in vivo. So here I'm showing you some of the results that we obtained. Essentially, the DLS tells us that regardless of what types of polymersomes we made, cross-linked, non-cross-linked, with drug, without drug, there are small differences in the size of all of them. And the TEM images actually shows the nice membranes of these polymersomes. And in order to summarize all the types of different nanoparticles that we made, for the polymersomes, for the non-cross-linked ones, we made some as a control, so we didn't load them with drugs, and we loaded doxorubicin in some of them in order to see how they will behave without cross-linking. And also, we cross-linked some of them, and then we compared these to the non-cross-linked ones in terms of the unloaded ones, the ones that are loaded with doxorubicin in its hydrophilic form, the ones that are loaded with camptothecin, which is highly hydrophobic drug, and ones that encapsulate actually hydrophobic and hydrophilic drugs at the same time, doxorubicin and camptothecin. And all of these combinations, we tried non-targeted and also EGFR-targeted versions of nanoparticles. So essentially, we had a lot of nanoparticles to play with and to study in order to understand how they behave. Now, the question is, how stable are these nanoparticles and how does the cross-linking affect their stability? In order to study this, we incubated our nanoparticles in media that has 50% proteins. And then we incubated these at 37 degrees in an incubator and kept observing the intensity with DLS at different time points. And this experiment actually lasted for 15 days. In these 15 days, you can see that the polymersomes, regardless of cross-linked or non-cross-linked, they degraded into smaller micelles. And then also they have degraded into larger aggregates. And in the TEM images, actually, you can see that we have a lot of transitions from polymersomes into smaller micelles, especially when the nanoparticles are non-cross-linked. And now the question is, can we apply this actually for delivering the drugs into cells? So in order to do this, we ran a number of cellular association studies, and we found that all the ones that has EGFR, they actually bind to the cells in a better way compared to the ones that are non-targeted at all or the ones that have negative targets. The other question is, do these nanoparticles release the drug? They are highly stable, but can they release the drug? The answer is yes. Here I'm just presenting to you the results of the polymersomes that encapsulate camptothecin and doxorubicin. And you can see clearly that we have more release when we have acidic environment, which is actually perfect for the tumor environment. And also you can see that doxorubicin actually is released more in the acidic environment compared to the neutral. However, for the camptothecin, it releases more than dox in the neutral environment, just because camptothecin dissolve so well in at pH 7.5. And can we prove this actually with confocal microscopy? The answer is yes. We have obtained some live images of the cells after 2 hours, and we have noticed that the camptothecin and dox, both of them were able to enter the membrane of the cells. However, the cells apparently tend to not like these nanoparticles, and they tend to split them into their blebs and their vesicles. And thanks to Diwan and Dosh, my teammates, for helping me with these results. And now the question is, how safe are these nanoparticles and how toxic they are? So to test this, we tried the control nanoparticles, the ones that don't encapsulate any drugs, and we found that actually they stay safe even at higher concentrations, which is exactly what we want for the nanoparticles. We want them to be non-toxic. Now, when we encapsulate the drugs within them, we can see that whenever Redox is introduced in high concentrations, it's actually able to kill the cells. However, the ones that has EGFR attached to them can bind more towards the cells. For camptothecin, we can see that it's way toxic than doxorubicin, and the ones that have EGFR have almost similar performance as the ones that doesn't have it. Combining these both, doxorubicin and camptothecin together in one carrier, shows that the ones with EGFR actually kills the cell more than the ones that are non-targeted. And the results actually with camptothecin alone are much better than the ones with the combination of drugs, just because the concentration of camptothecin in the one that has both of them is slightly less than the one in here. But effectively, if we have the same concentration, then they're going to kill the cells just the same. And thanks to Amber for helping with these experiments. Now, the question that we started with, were we successful in degrading the undegradable? Well, in order to test that, we incubated the sample that, this is just the results for non-cross-linked micelles that we synthesized earlier. So we incubated this one at room temperature in water, and we kept measuring the DLS to see if there is any changes in that. So for 15 days, we noticed that there is actually any change in the size. There is almost no swelling happening. So we kept the experiment running for even longer. And after 1.5 years almost, we noticed that there is actually swelling in the size of the micelles. Like they increased from 25 to almost 60 nanometers. And when imaging this with TEM, we found that the dye was able actually to go inside the nanoparticles much easier, which indicates that they are actually swallowing. They are actually able to allow more of the dye to go inside. And we were able to capture some polymersomes formations in this. And in order to make sure that actually this is what's happening and to know what's the fate of the polymer that we started with, we tested this GPC. So after more than 1 year, we found that most of the forming blocks have degraded into smaller units. To confirm this further, we did some NMR test of the polymer. This is actually after taking a sample of nanoparticles, freeze dry them, and then dissolving the polymers in chloroform. We found that in the 2D dose NMR, we found that we have several peaks, several strains of polymers compared to only one for the forming blocks, which means actually we have degradation. And all of these diffuses less than this one, which means that they are actually lighter, they are smaller entities. So that's good. Do we have more confirmation? Yep, the answer is yes. We did a spiral TE off and found that we have different types of polymers in here. Each line of these means that we have one different species of polymers. And here we have different number of in groups in this population, which means actually, yes, we managed to degrade the polymers. So in short and in summary, we were able to make high performance degradable diblock polymers. And from these, we were able to make high stable nanoparticles that are pH sensitive and can attain controllable release. And we found that the release increases with lowering the pH or using non-cross-linked nanoparticles or having micelles or doxorubicin. And we have perfect cellular association when the nanoparticles are targeted and the nanoparticles themselves are non-toxic. And now we are looking forward to doing in vivo experiments and see how these systems will perform in vivo. So at the end, I would like to thank my supervisors, Chris, Craig, and Nick, and would like to thank all Thurict group members. I would like to thank my family and all the funding bodies. Thank you.
Thanks, Salma, for a very nice talk, a very exhaustive study that you're able to do there. We've got 1 minute, so I'm going to ask one of the questions that's popped up in the chat. There's a couple there, so you might be able to answer them online afterwards. But the diblock polymer that you made was done via click reaction.
Yep.
Is it possible that you could use the ring opening radical reaction to grow the diblock directly from the macro CPA?
We can do that, but just we wanted to make sure that the conditions are well controlled and we don't include more steps in the synthesis. So, and also click reaction, because you know that whatever you have will be clicked. We're not going to have any side reactions. We're not going to have purification steps furthermore. So that was just for that.
Excellent. Well, like I said, there's a couple more questions in the chat. You can either answer those directly or we can forward them on so that you can answer them afterwards. Thank you for very interesting.
Yeah, sure. Thank you.
Okay. So moving on to our next speaker. So we've got Tan Nguyen, who is a postdoctoral fellow from the University of Michigan. So staying up nice and late so that they can give a talk here for us today. And so Tan's talk is Advanced Functional Polypeptides for Biological, Energy and Electronic Applications. So over to you, Tan.
Can you guys see my slide okay?
Yep, we can see your slides and we can hear you clearly.
Okay. Hi, my name is Tan, and I'm currently a postdoc in the McNeil group at the University of Michigan. And thanks for this unique opportunity to present my research to the audience in Australia. And this talk will serve as an overview of the work I've been doing. I did in the Gully group at Texas A&M University. So this talk will focus on the use of advanced functional polypeptide as material for hydrogen scaffold and as active material for organic radical batteries and flow batteries. So in the first project, we aim to make 3D cell cultures as extracellular matrix mimic to provide the cell with mechanical support, bioactivity, and anchor for cell migration. So there are several advantages for 2D cell cultures compared to the conventional 2D materials, including tunable stiffness, growth factor gradients, and diverse set interactions and phenotypes. And to do so, we synthesize pegylated alkene-functionalized polypeptides with varying hydrophobic blocks. And in the past, these polypeptides were demonstrated to form hydrogel upon heating. And our hypothesis is that the longer the hydrophobic block, the shorter the time and the lower the concentration it will require for the hydrogel to form. We first studied the rheology of the polypeptides in cell media, and it appeared that the block 30 polypeptide at 4% is the most promising for cell cultures. Indeed, this conformation can form the gel at a reasonably slow rate with an hour of incubation, and it was also injectable and self-healing. So these properties are revealing for cell culture study. So to fabricate the cell cultures with the P30 4%, we first homogenize the polypeptide in cell media, then mix it with the cell, followed by plating as droplet on the culture dish. All happen at low temperatures, and the droplets will let to gel up over an hour at 37 degrees C, followed by frozen imaging to monitor the cell proliferation over time. So these are the frozen images of the hydrogel after 1 day, 5 days, and 7 days of incubation. And we can see that the cells were able to grow inside the droplets even after 5 days. And when they reach the maximum capacity of the droplet, they evade to the outside onto the glass substrate. And this is the zoom out image of the cell at glass gel interface. And it appears that when the cells are on the glass substrate, they afforded elongated shape, and when they become more spherical when they are with the gels. And these studies are the first step toward a bigger plan, which is to develop injectable hydrogel for the treatment of spinal cord injury. And this is the ongoing work in the Gully group in collaboration with Dr. Jennifer Doolin at the biology department. So from this point on, I will switch gear to a completely different topic, which is the use of polypeptide as active material for organic radical batteries and the flow batteries. And our driving force behind this project is the interest in tackling some of the problems of conventional lithium-ion batteries, including the scarcity and toxicity and the increase in prices of the resources used to make the batteries, such as cobalt or nickel. Other issues that have been discussed more recently is the safety of these batteries and the use of child labor in mining precious metals. So one way to tackle this problem is the use of organic material, typically the use of redox-active polymers. Shown here are some examples of the redox-active polymer that have been used to make batteries. So our group is specifically interested in the use of tempo, radical, and biologens moieties because of their air stability and also because of the high oxidation potential of tempo and the low reduction potential of the biologen moieties. So our goal here is to bring these two moieties together to make organic radical batteries. And so this is an illustration of the organic radical batteries with the polymers carrying the tempo radicals in the cathode and the polymers bearing the biologen moieties in the anode. So these moieties have been incorporated onto a variety of polymer backbones, and here's example of some of them. So they can be classified into two subgroups, the non-conjugated polymer and the conjugated polymer. In terms of conformation, it appears that the conjugated polymer, the non-conjugated polymer don't have any well-defined structures, while the conjugated polymer can be helical in the case of polyacetylene, or they can be rigid rod in the case of paraffin-based polymer. And one feature that all of these polymers share in common is that none of these polymers are degradable. So our goal for this project is to develop degradable polymers that can be used for batteries, and also develop a systematic study to look at the effect of the polymer structures on the transfer kinetic of the electrons. And this is also when we think about polypeptide. So in nature, peptide can afford a random coil, alpha helix, or beta sheet. And according to a paper published a few years ago, the optimal distance between the two electrons, in order for them to hop from one to another, is about 6 to 7 Armstrong. And if we look at the structures of the alpha helix and the beta sheet, we could see that in an alpha helix, the distance between the two turns of the alpha helix is about 5.4 Armstrong, and the distance between the two strands of the beta sheet is about 3.5 Armstrong. So our hypothesis is that by using polypeptide, we can somewhat exploit the secondary structures of the polypeptide, and will reduce the distance between the electrons and facilitate the hopping in the polymer network. And with that in mind, we aim to convert small molecule amino acid into active polypeptide, then assemble them into organic radical battery. And at the end of life of the battery, we also want to degrade the polymer back to the starting material. So we started with glutamic acid as the starting synthon, and it was at first a challenge to bring the tempo moieties onto the polypeptides due to difficulty in purification, low conversion, and side reactions. So we ended up synthesizing the thiol-functionalized methylated tempo precursors with the thiol-functional group to allow for the thiol click chemistry to happen, and the methoxy group will act as a protecting group to prevent thiol reduction of the nitroxide radical. So the synthesis is quite simple, just by mixing the propargyl containing polypeptide with the thiol molecule together to make the precursor polypeptide, then exposing this precursor polymer to an oxidizing agent to regenerate the radicals. So on the other hand, the synthesis of the biologen polypeptide is more straightforward, starting with the chloro-containing polypeptide, which underwent sequential nucleophilic substitution to bring in the biologen moieties. So after we had the two redox-active polypeptide, we assembled them together into the organic radical battery. So this group is in collaboration with Dr. Children Luckenhaus group. And so at the top is shown an illustration of the battery setup, which we often call the sandwich cell. So this battery possesses two voltage window of 1.1 and 1.6 volt, and it can reach a maximum capacity of 38 milliamp hour per gram, which is a good starting point. However, the battery can only retain 18% of the original capacity due to the dissolution of the polymer into the electrolyte. So our next question is that, can we take advantage of this high solubility of the polypeptide in a different setup? We then collaborated with Dr. Susan Odom group to assemble polypeptide redox flow battery. The take-home message here is that by switching to a different setup, we were able to retain the capacity up to 93% of the original value after 250 cycle, and this number is 60% after 500 cycles. And also, lastly, we demonstrated that we were also able to degrade the polypeptide back into their starting material using a combination of liquid chromatography and mass spectrometry. Even though not shown here, we also demonstrated that both the polypeptides and their degradation product express low toxicity to different cell types. And to compare our system with other systems out there. So this table is summarizing some of the battery that have been made so far, even though there is remain more work to be done to improve our performance. We excited that we are among the first group to report a system that not only is degradable, but also provide opportunity for tuning structure, property, performance parameters. And this is the scope of the ongoing research in the Woolley group in the collaboration with Dr. Julia Luckenhaus and Diane Tabor to look at different conformation of the peptide to transfer within the polypeptide network. And to wrap up my talk, I would want to quote my PhD advisor. So we have to be careful about the plastic we're making in the lab. So with my research, I hope that future material design will take into consideration of material recyclability. And with that, I would want to thank my advisor, my collaborators, mentors, and the research group from my PhD study, and also the funding agency for funding my research. And I would want to thank you all for the listening, and happy to answer any question.
Thank you, Dan, for a very, very interesting talk, and thanks for joining us from the other side of the world at the moment. Do we have any questions? We've got a couple of minutes left there. If anyone's got a question, I might start off. I was quite interested to see that with your system, especially when you're comparing to the other systems, you showed that you had two different output voltages. So what's the second output voltage? So why do you see 1.1 and 1.6 for these systems?
It was breaking up. Can you repeat the last part of your question? I
said, so why do you see the 1.1 and 1.6 voltage outputs for these systems?
Oh, because the by origin having two redox processes. So it's starting as a 2+ and it can be reduced to 1+ and then 0. So that's why we can see two output potential. One. So let me go back to the very first slide. Okay. So on this slide, so you can see that the by origin here can be reduced from 2+ to 1+. So that's the first 1.1. And from this 1+ to the 0 neutral species, that's the second one. When we put them against the temple, that make it like 1.1 and 1.64 window.
So does the capacity? So does the stability of your battery depend on which one of those you're accessing? Because I guess because the tempo is only a 1-electron system, you could only access one of those. So you might have wanted to have a higher voltage at 1.6, but is it more stable if you only access the 1.1 voltage redox?
So our capacity, like you're correct that like our capacity rely heavily on what processes we can go down to. But for our system, the biggest problem is the dissolution of the material into the electrolyte. So like we thought about decreasing the window voltage, but with the dissolution, it doesn't really matter like what window we approaching. It always happen. The capacity always like like fan too fast. So
Okay.
I think that's the biggest problem we have right now.
Okay, so that's just about all our time. So thank you once again for joining us for that talk. So thanks, team. Yeah. Okay, so our next speaker for today is Yeasmin Nahar, who's a PhD candidate from the University of Tasmania. We've got Yeasmin, excellent.
Yes.
And so Yeasmin's going to be speaking today on the preparation of thermoresponsive hydrogels via polymerizable deep eutectic monomer solvents. So feel free to share your screen and start when you want to, Yeasmin.
Yep. Can you see my screen?
Not yet.
Sorry. That? Can you see my screen?
No, not yet. Just see you at
Sorry.
the moment. No, you're okay.
I don't know. I didn't find my sharing option.
Should be either at the bottom of your screen or top of your screen, depending on how you have Zoom set up.
Should be a big green
Button.
square with an arrow in it.
I'm sorry. Next on.
There we go. That's working now.
I'm very sorry.
No, that's okay.
Okay. Thank you very much. I'm Yeasmin Nahar. I'm going to present my presentation today on preparation of thermoresponsive hydrogel via polymerizable deep eutectic monomer solvent. And first, before going forward, I want to say what is deep eutectic solvent actually. Deep eutectic solvent is a mixture of two or more solid components. Among them, one is hydrogen bond donor and another one is hydrogen bond acceptor. So in their eutectic, they turns into clear viscous liquid with freezing point depression. And there are several types of deep eutectic solvent. They are formed by the components. One of them may be quaternary ammonium salt, sometimes metals like that. And but mostly interested one is quaternary ammonium salt and a hydrogen bond donor. Here are some common examples of deep eutectic solvent. The mostly used hydrogen bond acceptor is choline chloride. And here you can see some other hydrogen bond donor groups. And you also notice that this choline chloride and urea, their melting point is 303 for choline chloride and urea 134 degrees centigrade. And their mixture of 1:2 ratio at 80 degrees centigrade, they form a clear liquid, which is liquid at room temperature. You can see the freezing temperature is 12 degrees centigrade. While if you use acetylcholine chloride, it's more reactive, and this can form with urea, their freezing point is -14 degrees centigrade. And by changing this hydrogen bond acceptor and hydrogen bonding donor group, we can alter the solvent properties of both two. And why actually we are using deep eutectic solvent? There is a growing interest towards the application of green chemistry principle, not only in polymer science, but also in organic synthesis and some analysis. For the aspect of this, the environmentally friendly deep eutectic monomer solvent has arisen. It's very easy to prepare and purify, It's low toxic in nature, and also biocompatible, biodegradable, and also non-flammable. That's why nowadays it's using in various sectors. Diprotic solvent in polymerization technique. Diprotic solvent can be used in polymer as a solvent, as a monomer, or as a templating agent. At first, diprotic solvent can be formed. Maybe it can be polymerizable, or sometimes you can use as a solvent to form hydrogel or porous phenolates, molecularly important polymers, or polyhypes. Our target was to prepare thermoresponsive polymer from diprotic monomer solvent. And here you see we start from the scratch. Like at first we prepare diprotic monomer solvent from solid N-isopropyl acrylamide and a salt like choline chloride. And then after heating and stirring below its melting point of indivisible component, we get the clear liquid. This is diprotic monomer solvent. We termed it as a polymerizable because after using cross-linker and also pre-radical initiator or potassium persulfate, we got those thermoresponsive polymer hydrogel. And we also use acetyl choline chloride, like as I showed you, acetyl choline chloride and urea 1. We got this, those acetyl choline chloride and N-isopropyl acrylamide diprotic monomer solvent also formed. And we also prepare those polymer hydrogel from this solvent. This is the thermogravitic analysis data in the lower figure, it's B on the left-hand side. This thermogravitic analysis data of napalm choline chloride and napalm acetylene choline chloride diprotic monomer solvent relative to their starting materials napalm, they said that they are most stable than their starting materials. We also evaluate those freezing temperature minima, and we find that those napalm choline chloride diprotic monomer solvent has freezing point at 39 degrees centigrade, while with acetyl choline chloride, those diprotic monomer solvent freezing point minima is only 15 degrees centigrade. Differential scanning colorimetry data. On the right-hand side, it showed that yes, with choline chloride and napalm diprotic monomer, the melting point is 57 degrees centigrade, while we ran several run through the DSC, and then we find that the average melting point was 53 degrees centigrade, while the melt crystallization was 39 degrees centigrade. Also with the acetylene choline chloride and napalm, they support those visual one. One-dimensional protein NMR spectra are observed to support chemical nature of the formed diprotic monomer solvent. And we have noticed that the diprotic monomer solvent, after formed, we added it to the deteriorated water and just vanish those eutectic nature, and they give the NMR spectra is same as like D, as same as C. Those C spectrum was taken only the mixture in a diprotic monomer in a NMR solvent, and the number D was diprotic monomers in an NMR solvent, but there was no change in their chemical shift or anything. Then we take it in different way, like we take the NMR solvent in a sealed capillary tube, while the diprotic monomer within the NMR tube, and then we got the NMR spectrum E, which showed that that yes, all the individual spectra was present there with a chemical shifting, and also the broad spectra. It's maybe because of the hydrogen bonding nature and also those chemical environment. Like as I say, that diprotic monomer solvent is very viscous, and also we take this NMR at a 55 degrees centigrade so that it can be liquid at the temperature, and it support that yes, those diprotic monomer formed by the hydrogen bonding. Then we prepare thermoresponsive polymer hydrogel from these deputative monomers. Those kinetic studies showed us that the conversion of polymer hydrogel from deputative monomer solvent was nearly 100% within 15 minutes, while the hydrogel prepared in water, the conversion was only 55% after 1 hour. So it was very faster. Those temperature-dependent swelling of the sole of this gel was observed by immersing in water, and we find that those deputative monomer-based hydrogel was having like low swell. They can absorb low water than those prepared in water. So they are, and also this equilibrium swelling capacity is greater in water prepared hydrogel than the deputative monomer one. The reason behind this maybe we later find that those hydrogel prepared in deputative monomer, they are highly cross-linked, and the one prepared in water, they are not that much cross-linked. And also they both of them, they produced the swelling behavior from deswelling behavior when I heated them from 22 to 40 degrees centigrade, and they are both of them, they have those LCST over 30 degrees centigrade. This is the SEM photos of them, and those hydrogel prepared and deputative monomer, those freeze-dried structures showed that they are more globular in nature, while those prepared in water on the lower bottom one, they are more fibrous, having porous morphology with large void. The rheological properties also showed that their elasticity, like the hydrogel prepared in deputative monomer, having higher elastic modulus and complex structure than prepared in water throughout this temperature range. We successfully prepared our polymerizable deputative monomer, and from this monomer we prepared thermoresponsive hydrogel with having mechanical strength and higher cross-link density. Our future target is to prepare, is to developing those materials via controlled radical polymerization, and also nanoparticle synthesis, and also potential application in 3D printing. I want to acknowledge my supervisor and Central Science Laboratory of University of Tasmania and University of Tasmania for providing my scholarship. Thank you very much. And I'm happy to share any question.
Thank you, Yeasmin, for a very nice talk. We do have time for one quick question. So there's a question in the chat, and they want to know whether the eutectic solvents, are they being used in any commercialized products such as coatings or binders?
So deputative solvent actually prepared in, can you ask me question again? Oh, okay.
They want to know that the eutectic solvents that you're using, are they currently being used in any commercialized products like in coatings or in binders?
Yes. Now there are a few articles that they always say that yes, we can use it commercially, and also as I said, you can, it's environmentally friendly. So yes, we can use it.
Excellent. Thank you very much again for a very interesting talk.
Yep. Thank you. Thank you.
So now we have our penultimate talk for the day, and that is by Feifei Liu, who's a PhD candidate from the University of Queensland. We've got Feifei, excellent. And her talk today is going to be about the targeted delivery of novel immune-boosting peptides to both tumour and immune cells using polymeric nanoparticles to manage lung cancer. So over to you, Feifei.
Thank you, James, for the introduction. Can you hear me clearly?
I can hear you and I can see your slides.
Oh, great. Excellent. Hello, everyone. My name is Feifei Liu. I'm from Saborio Group in University of Queensland, and I'm a PhD student working on a targeted delivery of novel immune-boosting peptides to tumor microenvironment using polymeric nanoparticles to be a potential treatment for lung cancer. So first of all, why we are interested in lung cancer? So lung cancer is one of 4 leading cancers causing high death rate in the world, with 1.6 million people died every year. In 2020, there were around 9,000 people died in Australia because of lung cancer. So tobacco smoking contributes to more than 80% of causes to lung cancer. Other than smoking, environmental exposure such as secondhand smoking, air pollution, occupational carcinogen, etc., also play a vital role in causing lung cancer. According to pathological and histological features, lung cancer consists of small cell lung cancer and non-small cell lung cancer. So non-small cell lung cancer occupies 85% of total cases, which is our research focuses on. And the current 5-year survival rate for non-small cell lung cancer is only 15 to 20%, which is very low. The current treatment area for the lung cancer patients mainly includes 3 areas, depends on at which stage the patients are diagnosed. But due to the complexity of the disease itself and the limitation of each therapeutic method, the survival rate remains very low for lung cancer patients. Very luckily, our industry collaborator, they developed a panel of therapeutic peptides. So when this peptide was treated with human PBMC, it can enhance the secretion or expression of very important immune modulating cytokines such as IL-2, IL-12, and CD28. This leading to the reinvigoration of Th1 immune response in the system. So this peptide have great potential to modulate the immune response to non-small cell cancers and other diseases. However, the preliminary data showed that the peptide distribution in lung is very low, and also it cleared out from body very fast. So the tumor accumulation and set-specific response are the major problem for their clinical translation. And this can be improved actually by the nanocarrier platform. Therefore, we hypothesized that a targeted nanocarrier delivery platform can deliver this immune boosting peptide into tumor microenvironment in a controlled manner, thus increase the accumulation of peptide and subsequently suppressing the tumor progression via enhanced Th1 immune response. So this data will be very valuable for the clinical translation of this peptide. So we use the pegylated nanoparticle as a carrier in order to understand the particle size in tumor in peptide delivery, tumor uptake, and penetration. We designed 2 nanoparticles at this stage, affording different size range, which is hyperbranch polymer. It's roughly less than 10 nanometers, and micelles, which can be somewhere between 20 to 100 nanometers for our study. And we also use the fluorescent dye to track our nanoparticle and the peptide in vivo. So first of all, we have successfully synthesized our hyperbranch polymer with peptide conjugates. The overall design of hyperbranch polymer is use raft polymerization technique to produce a hyperbranch polymer first, and then this polymer will be further modified to afford a DBCO end group. And then our therapeutic peptide will be covalently conjugated on our hyperbranch polymer while a strand promoted Alkane-functionalized cyclone addition chemistry. So at the end, we successfully synthesized this hyperbranch polymer peptide conjugates whose size is about 5 to 6 nanometers. And then we also successfully synthesized our micelle So the block copolymer we used for our micellization is PMMA PEGMA block copolymer. So PMMA was used to form the core of the micelle due to its hydrophobicity. And PEGMA was used to keep the consistency of the nanoparticle corona the same as hybrid polymer to achieve the similar in vivo behavior. And then this micelle was cross-linked via a disulfide bond to increase the stability of the system. So from the TEM image, you can see the first one on the left-hand side is there is a very obvious spherical shape was observed. And to prove a successful cross-linking for the system, we back-dissolved the non-cross-linked and cross-linked micelles into organic solvent, where you can see the second image on the left. The non-cross-linked micelle actually completely fall apart into linear polymer. But the last image on the right, the cross-linked micelle actually remains a spherical shape. And DLS measurement also proved the size change when those two particles back dissolved into organic solvent. And the last step is the same as hybrid branch polymer. We conjugated the therapeutic peptide on the surface of the micelles via copper-free click chemistry. Now we have these two nanoparticles. The question is, are they actually improve the tumor accumulation as we expected? So we used the fluorescent image to answer that question. We used the C57BL black mice, which is immunocompetent mice, and we used the Lewis lung carcinoma cell line, which is derived from C57 mice, to establish this allograft mice model for our study. But before material was injected into mice, we did the cytotoxicity study to prove the safety of our material. So other than tumor cells, we also use the Jurke cells to represent the immune cells in the tumor microenvironment. The MTS assay has shown when our material, when each component was treated with the cells, the components here, we mean the peptide, the free peptide or the polymer itself. You can see the cell viability remains very good, which means each component are non-toxic. And then we add our material to the cells, and you can see the results here. Our material is also non-toxic. And then we proceed to the biodistribution study. We injected our material into mice, and the mice, different groups was sacrificed at 4 hours and 48 hours. And the ex vivo semi-quantification analysis has shown that the hybrid branch polymer peptide conjugates has very similar biodistribution as the therapeutic peptide itself, which is probably because the size of hybrid branch polymer is quite small. It's only 5 to 6 nanometers, and it's very close to the nanofiltration cutoff. But if you look at the micelle peptide conjugates, actually it circulates much longer time in the bloodstream, and at 48 hours time point, the concentration of the particle in tumor is 6-fold higher than the free peptide. And we were very excited about this result. And this is even a non-targeted formulation yet. The accumulation at tumor site is only based on the EPR effect, the enhanced permeability and retention effect. So now we know the peptide is in the tumor, but where it is in the tumor. So to get insight of that, we fixed our tumor sample and we sliced it with microtome and observed under confocal microscopy. From this image, you can see the blood, the green color shows where the blood vessels are in the tumor tissue, and the pink color shows where our nanomedicines are. So now we know we have peptide in the tumor, and we know where they are in the tumor. But next question is the peptide still active when they have been delivered in the tumor microenvironment? Do they need to be cleaved off to be active? So in case they need to be cleaved off in the future, so we are incorporated enzyme cleavage sequence in our peptide, which is sensitive to the matrix metalloproteins, MMP. And this MMP has been reported overexpressed in many tumors. And literature also reported successful drug cleavage and specific response for this delivery formulation. So after peptide being conjugated on the polymer, we also looked into the peptide release. We have get some preliminary data show that the peptide can be successfully cleaved off, and the level of peptide cleaved corresponding to the different level of MMP in vivo. So if the peptide needs to be cleaved off in the future, we have options available. In conclusion, we have synthesized 2 nanoparticles for peptide delivery, and both of them are non-toxic. And one of them, which is the micelle peptide conjugate, has shown prolonged circulation time and enhanced tumor accumulation. So in the future, we have planned to look into the larger particle size, such as polymers, to see if there is more difference among different sizes. And also we are interested in looking at the targeted formulation, such as using small molecule or antibody as a targeting ligand. And all the formulation will be compared in terms of the therapeutic efficacy. And in the further future, we also are interested into looking at the combination therapy, such as combination with chemotherapy or antibody, such as PD-1, PD-L1. So that's all from me today, and thank you for your listening, and thank my supervisors team and my industry collaborator, Intercate Peptide Therapeutics, and thank you all the funding bodies.
Thank you very much, Feifei, for a very, very interesting talk. Unfortunately, we're running right on time at the moment, and I know that that people will have other meetings after this, so I'm going to have to go straight to the next talk. Thanks again for a great talk. If there's any questions, please put them into the chat, and we'll pass them on to Feifei so that she can answer them as well. But thank you once again.
Thank you.
Okay, so we're running just about on time, which I think deserves a huzzah. Our last talk of today is Amin Khodabandeh from the University of South Australia, postdoctoral fellow, and he's going to be giving his talk today on utilising raft polymerization for the preparation of well-defined biocontinuous porous polymeric support. So over to you, Amin.
Thank you very much, James. It's delightful to talk to you all today, and thanks for staying with me for the last talk for today. So this is my topic. It's work between the work is between the raft polymerization, and I'm going to show you why I'm doing the raft polymerization for preparation of the porous polymer, and also showing some application in separation science. It's only in 1 or 2 slides. So a background here that the polymer chemists are usually often use the size exclusion chromatography for analysis of the synthetic polymer. It's basically the analytes is injected to the column. Column is a heart of the system, and separation is happening based on the size of the polymer. The smaller polymer stay longer with the pores, and the larger one pass through the larger pores, and the separation is happening. After the separation, we can use the polymer standards to find the molecular weight and polydispersity, and also you can have access to the if you have access to the viscometer or a Mars detector, you can get the direct molecular weight. So basically what we have inside the column is a pores with larger pores and smaller pores on top of the larger pores. The trend here in the research that people trying to, scientists trying to reduce the size of the particle from 10 micrometer that is a standard now to the 2 to sub 2 or 3 micrometer in size to increase the efficiency of the work. However, why we can get a better separation and faster separation, the problem is coming with this method. First, the back pressure is increasing. The second, this back pressure could breakage our particle. And if you are using the Mars detector, this is going to be bad based on the bleeding that the particles comes out from your system. Our group studied the polymeric monoliths for a long time, and recently we reviewed the work about the polymeric monolith can be used as an alternative method for preparation of the SEC column. But the problem here, the good things here, that the back pressure is going to be low because of the follow-through pores. However, the recent, the current technology has no efficiency or less efficiency, especially for the oligomeric polymer separation. So if you search monolith on the internet, you can end up with a mysterious metal object that is coming and appear and disappearing. However, what I'm talking today is about a single piece of the polymer material with a porosity, and the analyte can go through this, and preparation is very simple. Use monomer and cross-linker, dissolve this in a pore-forming agent, and mixing this together with initiator, and after polymerization can be used as a single piece of the polymer. This mixture can also add it to the column and also can be polymerized inside the mold using GC oven, water bath, etc., etc. Okay. The IUPAC definition of the pores is important in my project. This is the IUPAC definition, but for the SEC column, we do need mesoporosity for selectivity. We do need macroporosity for permeability. We do need both together. And what we don't need is macroporosity. So reducing the macroporosity is the reason. And the first question here, can we prepare dual pores monolith with the current technology? And the answer is yes. There are 3 different ways, using only the cross-linker, or the other method is a hyper cross-linking method, and also polymerization induced phase separation. But in my project, I'm introducing or investing my time on designing a new method for preparation of the dual pores, and the question here, why I'm bothering. In my group, since 2015, we studied different methods, the cross-linker monomer and hyper cross-linking reaction, and this is the result from absorption-desorption technique, nitrogen absorption-desorption technique. I'm not going to details of this isotherm that you can see here, but exporting the data in the table, I would like to emphasize on the surface, BET surface area, and you can see most of this surface area comes from the macro porosity, which is below 10 nanometer, is not good for the SEC column. And interestingly, 85 to 96% of the total volume of the pores is coming from the pores that is not useful for separation science. Polymerization-induced macrophase separation in 2012, introduced by Hillmeyer group in US. And it's interesting material with the dual porosity, have the mesoporosity and have macroporosity. This is the method that they use for preparation, using the PLA CTA styrene dibenzene, AIBN, and polymerization can be done in presence of the PEO. But the problem here is the back pressure is very high due to the macroporosity is the PEO size is introducing the macroporosity, and there is a limit in here. And also the basic etching process here is not simple. 70 degree, 3 days using the methanolic pH 12 with sodium hydroxide is not easy to have access, especially when we polymerize inside a column. What I'm looking at the moment is, in my project, is using the same pore-forming solvent, monomer and cross-linker, by adding the raft agent to control. Not only the hypothesis is the raft agent is not only control the kinetics of the polymerization, but also control the pores of the obtained material. It's easy to use. This is my system using the styrene dibenzene with thermal initiator, CTA, and an organic solvent. The first thing we've done is a kinetic investigation, polymerizing the monolith precursor inside an NMR tube. And this result showing that when we don't have the CTA, the monomer conversion is happening very fast, but by adding the raw polymerization, we have a delay here. If I show this in the logarithm way, you can see that we have inside the polymerization first is fast, but then we have a delay in the phase separation, onset of the phase separation. This result is actually already observed by CSIRO group, gray mode from CSIRO group. And let's go to the SEM, scanning electron microscopy, showing that the material can be obtained with different concentration of the raft, with different shape and smaller pores. The bottom one has no raft agent, so next thing is introducing this inside a capillary or the column. So this is the cross section of the SEM of the cross section of the column. That's 200 micrometer size. I would like to only focus on these top two, no CTA at the left, and with the CTA, the raft agent on the right. And the nice thing here that the back pressure, which shows the repeatability of these, can be obtained much, much better when we are using the CTA. This is 7 times repeat of the same recipe in the different days. So this is a very interesting result. The next is using this for small molecule separation. Same column can separate the medium size molecules and also like peptides, and also we can go to the bigger one, which is proteins. And this is very interesting because at the moment, if you want to polymerize, if you want to analyze your material, you do need to order different columns for different kind of separation, but this single column can separate all of them in a different condition that I put it on the bottom of the each separation. Lastly, we would like to know if it's possible to change the type of the raft agent and change the concentration. Can we obtain a material with a high surface area and control over the pore size? This happened. And the bottom one is no CTA, and you can see the isotherm is not a great one, especially when you look at the surface area. But with increase the amount of the raft agent, we can get a higher surface area. But the important things here that we can get the type A or type E in the isotherm that you can see here that this consists of the open tubular pores, and the top one is the one with the bottle-shaped pore, so we can control over the pore and the shape of the pore as well. So the pore size distribution is brilliant for this type of material. The very nice, very nice pore size distribution, 10, 20, and around 50 nanometer in size. And this is currently is being using for preparation the actual column for SCC. So I'm hoping to show you that the RAC polymerization not only can control the kinetics of the polymerization, but also can control the size and also the shape of the pores. So as a summary here, CRP in my project has been used for preparation of macro and mesoporous polymer monoliths. This material has been used as a separation as a separation media for separating small, medium, and large molecules, and also the future work will be focusing on the SEC for separation of the polymeric material. And I would like to thank everyone in special thanks to the technical team at Future Industries Institute, and also the funding company, and also thanks James, Georgia, and Nathan for organizing this great event. Happy to take any question from you guys and audience.
Thanks, Amin, for a very nice talk. We've probably got time for 1 or 2 questions if there is any, and you want to put them into the chat. I've got one maybe to start with. I was just wondering, with using the chain transfer agent when making these monoliths as well, I mean, you're obviously getting the porosity you want, but what about the chemical interaction of having those end groups, either as the end groups or as they break down? How does that affect your porosity?
That's a very good question. Actually, Smart Ticket was one of the persons that asked me the same question. So we remove the end group through the typical end group removal process using the column. With and without this, when we're separating the small molecules, it's not affecting at all. But for peptide and proteins, yes. At the moment, I'm not sure about this effect on the polymer because I'm working on this, but definitely is affecting for peptides.
So for the end group removal, what kind of end group removal? So you're just doing aminolysis to leave a thiol, or what are you actually doing to?
There are a few different techniques for removing this, and one of them is using the high amount of the initiator.
Yeah.
So what we did, wash this with a high amount of the initiator and then put it in the GC oven, the whole column, and then wash out and look at what is coming out, calculate amount of so I have one slide, but not showing today, but yeah, it's possible to see the effect, especially with peptides.
Okay, excellent. Well, we don't look like we have any other questions at the moment, but I'm sure that if there is any, then they can get in contact with you and you'd be more than happy to answer those questions as well. Okay, so that brings our session to an end. So I'd just like to thank all of our speakers again, and all of our speakers who are still online. If you could hang around, Nathan's going to get some screen grabs so that we can take some photos for the Polymer Division as well. I'd just like to remind everyone that next week, February 15th through 19th, we have the Australasian Polymer Summer School. Hopefully many of you have signed up for as well, where you'll be able to get a lot more tutorial and workshop information for students and for early career researchers. And next Friday, I'm handing the reins over to Nathan, who's going to be chairing the session. On the website, it says that we've got a to be confirmed keynote speaker, so that'll be Beth Alakwa, who will be speaking as our invited speaker next week. We've got an excellent lineup of talks again, so it would be great to see many of you tuning in again. So thanks everyone for making the time to come along, and see you all next week.